Alright, this will be my first video ever. It's November 9th, it's Monday, 2015. I will put all relevant place names and coordinates in the description box so you can look them up afterwards. Alright, so what I'll be doing is I will be testing for the curvature of the Earth. I am standing in Kershaw Park at the north end of Canandaigua Lake in upstate New York. I am standing in front of the smaller gazebo on the west side of the park. The main park building and beach is over that way. That tree's in the way, so I'm going to walk down there later just to show you. Both those buildings can be seen with Google Satellite View or Google Earth. Okay, so what I'm going to do is I'm going to measure this railing in front of me here and how high it is above the water. Got my tape measure here. It's all set to go. Okay, so putting it in the water down there, and what we have is about, hopefully the video's okay there, 8 feet 7 inches or 103 inches. Now actually from the distance I'm going to be, which is 5.33 miles down at Gooding Point on the east side of the lake, from there I should not be able to see this railing. So that's what we're going to do. Right now I'm going to walk over to the main building just so you can see that I'm actually in Kershaw Park. Coming up on the main building there and the beach. Like I said, this is my first video. If I suck at filming, sorry about that. And so there's the main building. It's actually closed for the winter now, I think. But you can see the beach there. And there's the main building. Like I said, you can go to Google Satellite View or Google Earth and you should be able to see that one. It's on the east side of the park and the gazebo's on the west side. So right now I'm going to get in my car and I'm going to drive down to Gooding Point. Before I shut the camera off though, let me show you my crappy flip phone so you can see the date and the time, so you know how much time has passed. Hopefully you can see that. Yeah, it's kind of blurry. But the time is 1:52 there. There you go, zoomed in. Okay, Monday, November 9th, 1:53 p.m. Alright, I'm back. Sorry it took so long. There you go, 2:42 p.m. I am at Gooding Point. Over there somewhere is Kershaw Park. Here's my ghetto telescope set up there. I'm going to walk around after this. I'll show you Pelican Point Marina. They've got a cylindrical roof. You can see that on Google Satellite View. Okay. So this is a Meade, M-E-A-D-E, ETX90 astronomical telescope. Hopefully you can see that there. If not, I'll add a separate clip later. So we're about 2 feet off the surface of the water. Okay, so tape measure in the water. About 23 inches to the top of the telescope, so probably 21 to the middle of the telescope. But I'll just do 2 feet in the calculations. Okay, so without the tripod, which is way too tall, this kind of moves a little bit, so hopefully this will work. Should be all set up. If it'll clear up. That's it right there. As you can see the whole railing. So looks like the Earth might be flat. I'll try to take a still and zoom in on it maybe, give you a clearer picture. Alright, so I'm going to try to move this thing over and show you the main building, just so you can see it is Kershaw Park. There's a mirror in here that reflects it up to the eyepiece, so it's going to look like I'm going the wrong direction, but I'm actually panning to the east, or to the right. But it'll look like we're going left, so ready? So we're going left. There are the trees that were in the way before. There's the beach main building area. Lost it. There it is. Alright, so not the greatest setup, but that'll do. So I didn't see any curvature there. Again, I'll try to get a still out of that and zoom in on it and show you the railing. Right now I'm going to walk over to Pelican Point Marina. The docks on Google Satellite View are usually right there, but they're up for the winter. So you can kind of see it now. That's Pelican Point Marina there. Let's get the sign for you. Pelican Point Marina. Okay, all I have is my laptop microphone. Hopefully the audio quality is not too bad. Sorry about the shakiness of the telescope view in the video, and apparently my camera was also having trouble with the lighting level. So I was able to get a few stills though, so let's take a look at them. This is probably the best one. So right here is the whole railing. You should probably see a wall of water right at the railing line, right there, if the earth was actually spherical. These little rocks here, those are probably 2 or 3 feet off the water. See a bunch of them. We zoom in 200%. And it's not much better, but you can see that's the full railing right here. Got a few of them. I don't know if they're any better. Again, there's the full railing, rocks, full railing. Full railing, full railing, and here's the beach, a little washed out, but this is the sand right here. Shouldn't be able to see the sand, so Earth is looking pretty flat from these pictures here. So let's go to the calculations. So this is the Earth curvature shortcut formula. The height obscured equals the distance to the target from the observer minus the distance to horizon squared times 8 inches. Now if you guys have listened to other flat earth people talking about this formula, they don't mention this distance to horizon thing, they just say distance squared in miles times 8 inches. And that is not wrong, but it's for a observer height of 0. So if your camera, your telescope was in the water, floating on top of the water, that formula would be good then, but that's not practical. We need to get the camera or telescope above any present waves, plus you don't want to get your equipment wet, plus you've probably got a tripod, so we really need to include this term. So the height obscured, just to define all this stuff here, height obscured by the curvature of the earth in inches, you can divide by 12 to convert to feet. Anything shorter than this height should be hidden behind the curve of the earth. D target is just the distance between the observer and the target in miles. D horizon is this what's called the distance to horizon. It's in miles, and it's based on how high your telescope or your eyes are above the surface of the water. Some people also refer to this as the tangent line, and that has to do with the circle and trigonometry, circle math and trigonometry you have to do to figure it out. You don't have to do the math to figure it out though. You can go to Google, just type in distance to horizon calculator, and should be first or second one in your list. And this is ringbell.co.uk/info/hdis.htm. And so in this example, my telescope was 2 feet above the water. You put your telescope pipe in, say calculate distance, 1.7 miles. The only bad thing about this one is it only gives you 1 decimal place. So go back here. I actually did the calculation, it was 1.73, so I'll use that when we do the math here. I'll do another video where I'll show how to get this stuff without the shortcut formula in case you don't trust the shortcut formula or you want to see how it's actually done. It's not too complicated, but it'll probably be using math you haven't used since high school. But let's just do the calculation so I can get this video over with. I think we're probably at the 12 or 13 minute mark. Okay, so distance to target 5.33 miles, distance to horizon 1.73 miles, so I'm just going to subtract this from this. So that is 3.6 miles. If I square that, I get 12.96. If I multiply that by 8, I get 103.68 inches. And if I divide by 12, I get 8.64 feet. And the railing height was 103 inches, so it should not be visible based on the calculation.